Hello, welcome back. In the last video, I described how we can get a velocity equation when we have uniform acceleration. I call that Kinematic Equation 1. In this video, I want to, again, have uniform acceleration, and we're going to come up with an equation for position. And we're going to call that Kinematic Equation 2. That's not very creative. So let's go back. First thing I want to do is review kinematic equation number 1, just briefly, what that was. That said that if we had a constant acceleration, we had a graph of velocity versus time, and it was a line. And we had an initial height, v0, that would be the velocity. When time was 0, that would be how high the velocity graph was. And our slope was the acceleration. So when we wrote that as an equation, we had kinematic equation 1, which says the velocity at any time equals the initial velocity plus the acceleration multiplied by time. Okay, that was kinematic equation 1. In this video, I want to develop an equation for position versus time. That's going to be the goal. To do this, let's kind of think about how this would go. Roughly, what are we expecting? So let's see if we can sketch the graph. Let's assume maybe something starts at a height, at an initial position. So we're going to graph position. We have time. And let's think about what happens here. There's some initial position, x initial, because the height of the position graph when time is 0 is the initial position. And then, well, the only thing I really know is this graph right here, or maybe this equation, but, okay? So, to remind myself, say to myself, what does velocity tell me about a position graph? And then I remember that the velocity tells me the slope of the position graph. Let me write that down, just to remind you. Velocity is the slope of position versus time. Or, turn it around, we had that the change in position equals the area under velocity versus time. For right now, we're going to use the top one. In a moment, we're going to use the area concept. So over here, imagine this is my velocity. And at time 0, the velocity is small and positive. And then a little bit later, the velocity is larger and positive, and then larger and positive, and then larger and positive. Well, let's kind of sketch what that would look like. I guess I'll do that in green here. So at the beginning, the velocity would be small but positive. So maybe something like that. I don't have units there, but you can kind of imagine. Small and positive. And then later on, the velocity would be larger and positive. That means the slope would be larger and positive. So maybe it's like that. And a little bit later on, the slope would even be larger and positive. So maybe it'd be like that. And what we would get when we connect up these points is a curve which looks something like that. So I'm just sketching things. I didn't put numbers down, so we can't be too quantitative. But if I were to tell you to expect this velocity graph to correlate with parabolic or parabola curve, shouldn't be too surprised, and that's where we're going to end up. So think through how I did that. That's kind of a useful skill to have. At the beginning, the velocity was small and positive, so I just kind of dashed in a little line with a slight positive slope. And then the velocity grew with time and became more and more positive. So that means the slope should get steeper and steeper and steeper. makes it arc upwards. Okay. Now we're going to use the second relationship, the area relationship, and our velocity versus time graph, and we're going to turn that into a formula for position, function of time. I'm going to redraw this graph just because it's useful to have and it's not that complicated. And I know that this height is V initial. And after this time here, this velocity, and after time t, the height of the graph, well, at time t, the height of the graph would just follow along using the velocity equation. So it would be v at time t would be v initial plus at. So the height at time t, if I can get these things all kind of lined up, would be v initial plus at. That would be the height of the graph for velocity at time t. Okay? So this is a line, and so between time 0 and t, it ranges from v initial to the result of that equation, but that's v initial plus at. I'm doing everything symbolically because the goal is to come up with an equation which works no matter what. It'll work when the object is going up. It'll work when an object is going down. It'll work when an object is going right or left. As long as the acceleration is constant, these equations will work. They don't care about the directions of things. As long as the acceleration is constant, these equations will work. So to have such a powerful universal equation, I don't want to put any numbers in. I want to work it all out symbolically, and then we will have numbers that we can remember. I don't expect that you would reproduce this derivation on a test. I'm putting it there so that you see where it's coming from. I want you to see that it's not magic. There's a reason for this. Okay. So now, our relationship, the second one here, says that the area under the velocity versus time graph, this area, gives us the change in position. So that means this area, well, and I'm going to break it up into a rectangle and a triangle. If I add up the area of the rectangle and triangle, that gives me the area under the velocity versus time curve. And if I have that, I will know the change in position or the displacement. So let's do that. Well, let's handle the easy part first, the rectangle. Okay? The base of the rectangle would just be t. It goes from 0 to time t. The base is t. The height of the rectangle is v initial. So if I'm doing this, I'm going to say that the change in position is given by the area of the rectangle plus the area of the triangle. The rectangle is easy. That's a base times a height. The base is just t, and the height is v initial, the initial velocity. So that's going to be v initial times t. Swap it. That's how I prefer to do it. Okay. What about the triangle? To find the triangle, I just use the formula for the triangle. The triangle is here. The formula for the area of a triangle is 1/2 the base times the height. The base for the triangle is the same as the base for the rectangle. It's t seconds. What about the height? What about the height of the triangle? Well, the height of the triangle would be just this height. You don't want to include the bottom of it. So that would be V initial plus AT minus V initial. That's just going to be A times T. So the base of the triangle is T. The height of the triangle is A times T. I pull it all together, and I get that the area of the triangle is 1/2 T times AT, or 1/2 AT squared. I just can pull it together. The change in position, formula for the change in position, whenever the acceleration is constant, is, as a function of time, is delta x equals V initial t plus 1/2 AT squared. Or one last little wrinkle. That's a perfectly fine equation. We will use this a lot. So this is a good one to know. Just to make this equation look a little bit more like the first kinematic equation, I will remind you that the change in x is the position at time t minus the initial position. So I can write this as x minus x initial, or I can rearrange it to say the position at any time, the position at any time is the initial position plus the change, which is this stuff. And this is our second kinematic equation. So I'm going to call this one Kinematic Equation 2. K EQ. Sometimes I do just KE, but I think I do KE. Kinematic Equation number 2. This is an equation where if you know the acceleration and you know the time, you can find the position, or you can solve it. You can bring all the power of your algebra skills to bear on this. So it's a relationship between position and the initial position, the initial velocity, time, and acceleration, assuming acceleration is constant. Notice, what kind of graph is this going to produce? What kind of curve is this? If you think of this as a function of time, so remember, x initial, that's the initial position. It's just one, it's a number, it's a constant, it never changes. The initial velocity, that's also a constant. So these are just constants, and acceleration we are assuming is constant. So the only thing that changes in this one, as the object moves, is time. Everything else is constant. So constant, constant, time, constant, time. What kind of graph would that be as a function of time? That's just a parabola, as advertised up above. Okay? So Kinematic Equation 2 says that when the acceleration is constant, you expect the position versus time graph to be parabolic. It will turn out, if the acceleration is positive, it'll be concave up. If the acceleration is negative, it'll be concave down. We'll go through all the variations when we go through examples, but this is the equation which describes position versus time graph for uniform acceleration. In the next video, I'm going to introduce our third kinematic equation, and then we're going to take a lot of time practicing, learning how to use these equations, how to get intuition, and understand how they all come together with the graphs, with the definitions, and with all your algebra skills. And we can use all that to solve problems. Thank you. See you next time.